The beginning of the 20th century was marked by an intensive industrialization period, both in Europe as well as in America. There was no let-up in building plants, bridges, roads, and skyscrapers. Soon, questions on the quality of the construction and standard construction practices became a concern. One vulnerable part could become a cause of a major accident and serious casualties. In 1928, Russian scientist and professor Sokolov suggested the use of the ultrasound method to control the quality of construction projects. The method was simple in theory. A piezoelectric transducer converts electrical pulses to ultrasonic ones and transmits elastic vibrations into the object. The ultrasonic waves propagate into the material and reflect from the opposite back wall or from internal discontinuities. The reflected waves are received by the same or by another transducer and are displayed as an echogram. Interferences along the sonic path influence the results in the echogram. By analyzing the reflected waves, it is possible to estimate the condition of real objects. The ideas of the Soviet scientists were put into practice rather soon. Since the 1950s, ultrasonic testing has been used primarily to test steel structures. The situation with the key building material was trickier. Unlike steel, concrete is a very heterogeneous material, composed of cement, sand, multi-size aggregates, and water. When an ultrasonic wave propagates through this medium, the incident and reflected waves are weakened by the attenuation of the signal in the concrete matrix. Decades were spent to invent a simple and handy device capable of estimating quality of concrete constructions with ultrasound. Developers worked hard on both sides of the Atlantic. But even at the dawn of the third millennium, the world continued to witness numerous accidents related to deficiencies in the construction of reinforced concrete structures. The test results are shown as a typical B-scan, cross-sectional image of the area below the antenna along the plane parallel to the longitudinal axis of the antenna. The image can then be further post-processed and analyzed along any given plane using a personal computer. The image showing the internal characteristics of the test sample is visualized as a perspicuous color map. Every point in the zone of testing is depicted as a certain color scale, depending on the intensity of its reflection. Every reflector's position can be located with a high degree of accuracy. The tomogram shown was obtained from tests performed on fireproof plates of a glass melter. At a nominal depth of 130 millimeters from the surface, a cylindrical-shaped flaw, approximately 750 millimeters long, can be observed. The following tomogram shows a red zone corresponding to a voided steel duct in a concrete column. The test results were confirmed after performing an exploratory opening. To understand the test results, but full appreciation for the Mira equipment is evident when 3D models of the test results are generated.
The new Mira system is, in my opinion, the most advanced ultrasonic system for inspecting concrete. First of all, it's an imaging system. You get an image of the interior of concrete practically in real time after you do measurements.
The axonometric image reconstruction makes it possible to readily discern internal flaws. It could be more evident only if the concrete would have been turned into glass. Numerous trials at independent scientific centers were an indispensable part of the Mira development. One of these proving grounds was the Federal Institute for Materials Research and Testing in Berlin, Germany. A concrete block with embedded steel ducts was tested to determine the accuracy of the 3D image reconstruction software. The tests were performed by engineers and specialists experienced with ultrasonic testing and the Mira system. A non-destructive testing engineer from Chicago, Mr. Aldo de la Haza, scanned the block's surface. He was followed by Dr. Herbert Wiggenhauser, an NDT specialist from Berlin. When all tomograms were collected, the mirror system was connected to a laptop and the collected data was transferred. A proprietary software provided with the mirror device processed the data, and the 3D reconstruction of the test specimen was displayed on the computer screen. The virtual model strictly corresponds to the geometry of the real object.
The second generation of the mirror seems to be very promising technology that is going to allow us fairly quickly produce images of the concrete structures and internal flaws.
Ultrasonic testing of a concrete wall panel was performed using the mirror system to measure the thickness of the wall. At about 3 to 4 seconds after the system was triggered, the test results were displayed on the built-in screen. The bright red area in the tomogram corresponds to the signal reflected from the back wall. The thickness of the concrete wall panel is indicated by placing the cursor at the center line of the red spot and reading the corresponding depth on the metric scale on the left side of the tomogram.
This is a very, very promising system for a number of applications, starting from simple thickness measurements to measurements of, for example, tendon ducts. Even reinforcement can be inspected with that.
The third sample tested was a reinforced concrete slab with reinforcing bars placed at various depths. The results of the mirror testing show the location of the first set of bars at about 50 millimeters. In this tomogram, the bright red area at about the 200 millimeter mark corresponds to a reflection from the bottom surface of the slab. Above this reflection, 3 additional red spots are shown. These spots are reflections from bars located directly under the antenna array. The metric scale on the left side of the tomogram shows the location of the reinforcing bars at a depth of 50 millimeters from the surface. The next tomogram shows the location of the next set of bars at about 30 millimeters from the top of the slab. Physical measurement taken at the edge of the concrete sample confirmed these findings. Since 2009, the ultrasonic shear-wave tomographic mirror system has been purchased by private companies and research institutes worldwide.
Increased number of transducers has led to improved resolution of the images. The screen allows you to look at your results while you're testing.
People said it is a wonderful instrument, and compared to other methods, you can solve many other difficult applications.
The mirror system gained acceptance at a federal level in Russia in 2010 when it was used to test the bridge connecting Vladivostok and the Russky Island. This is one of the most important bridges and carries national significance. Developers of the Mira ultrasonic tomograph system aspired to create a device that would raise the non-destructive testing of concrete to a much higher level. It looks like they succeeded. Mira is the only ultrasonic tomography system that doesn't require the use of a coupling agent. It's the only system that can measure the thickness of a reinforced concrete member up to 2 meters using a one-sided axis. The software with the DFA algorithm provides high resolution and high speed of measurement. The operator can see in the built-in TFT display a comprehensible color scheme of the internal characteristics of the test sample. Thanks to the DFA, an accurate 3D model of the inspected area can be reconstructed. Experienced NDT specialists are already using the mirror system all over the world. English, French, German, Spanish, Turkish, Polish, Chinese, and Japanese languages are available in the menu interface. The innovative ultrasonic tomograph is currently used during the reconstruction and inspection of dwelling houses and industrial buildings, bridges, tunnels, tanks, and other structures. The device is capable of finding voids, delaminations, and cracks in stone and concrete. It measures the thickness of concrete blocks, determines the location of reinforcing bars at various depths, voids in tendon ducts with pre-stressed strands or rods. It is a useful tool to estimate